Performance of synchronous motors. The synchronous motor, how it performs in different conditions and different. Yes, now objectives are the performance of synchronous motor on no load. That means there is no losses in the motor, and the performance of synchronous motor on no load with losses. Here these are two ways: no losses with losses, and the synchronous motor on load. So, and the analysis of phasor diagram. Analysis of phasor diagram. Synchronous motor behavior on load. When load is increased, on DC motor, the speed of the motor reduces. The load is increased on the DC motor, the speed of the motor reduces. So, now in a DC motor, armature develops EMF which opposes the supply voltage, that is called V, that is voltage which opposes the supply voltage V, that is called back EMF EB. Here the resultant voltage across the armature is V minus EB. The resultant voltage across the armature is V minus EB. Here it causes an armature current given by the expression, that is IA is equal to V minus EB by RA. In DC motors, so armature current, that means here, so EB back EMF is established in the armature, then it opposes the it opposes the supply voltage. When this back EMF causes an armature current given by the expression. So now that IA is equal to V minus EB, this causes, so current given, this causes an armature current given by the expression IA is equal to V minus EB by RA. So now where RA is armature resistance, and EB is back EMF, that is nothing but pi Zn by 60 into P by A, pi Zn by 60 into P by A. Now the back EMF in a DC motor, depends on the armature speed. Here the N is the speed, so EB is proportional to N. So back EMF depends on the armature speed. So now in a synchronous motor, back EMF is set up in the stator. The back EMF depends on the excitation given to the field only. Here it does not depends on the speed, because the speed is constant. It does not depends on the speed. So here, because the speed is constant. Similarly, similar to the DC motor, the armature current for the synchronous motor is given by, armature current for phase is IA is equal to V minus EB by ZS. where Zs is equal to Ra plus Jxs, Ra plus Jxs. So, synchronous impedance. Ra is stator resistance per phase, Xs is synchronous reactance of stator per phase, V is equal to supply voltage per phase, Eb is equal to back EMF per phase. These all are in per phase manner. Here the synchronous motor on no load, that means here within bracket given no losses. No losses means here it is no losses means it is identical machine. Generally we assume that. Here when the motor running on no load with field excitation, it is assumed as no losses. The magnetic locking between stator and rotor is such a way that the magnetic axis of both coincides with each other as shown in figure. See, observe this one. S, NS, NS, S these are coincide each other. This is the no losses assumed cases. So now the back EMF Eb is equal and opposite to the supply voltage V shown in figure. So supply voltage V in X positive direction, Eb is X negative direction. If Eb is equal to V, no armature current. Why? Here V is equal to Eb, both are same. So now armature current Ia is equal to V minus Eb by Zs, so which gives the results in 0 current. But the vector difference of V and Eb is 0. V and Eb is 0. So now this is the hence Ia is equal to 0. Ia is equal to 0. So it is normal excitation. It is normal excitation. Now motor takes no power as there is neither load nor losses. So in practice this is impossible. So in actual practice it is not possible. Somewhat the armature current draws the stator. So motor has to supply mechanical and iron losses along with small copper losses. So when synchronous motors is running on no load with losses, the magnetic locking exists between stator and rotor, but there exists a small angle of difference between the two axes of magnetic fields shown in figure. See the figure. This is the figure. See, synchronous motor on no load with losses now. Say observe this one. Here NS and NS means the stator pole with synchronous speed and rotor pole with the red north and south pole with the synchronous speed of stator, and here the rotor speed is, so fall down some what, so here some certain angle. Synchronous motor on no load with losses, here the rotor axis falls back with respect to stator by an angle of alpha as shown in figure. So here this alpha decides the amount of current required to produce the torque to supply the various losses. This angle, what says this angle? This angle alpha decides the amount of current required to produce the torque to supply various losses. So now hence the angle is called load angle or power angle or coupling angle or angle of retardation. So we can say different way, that is power angle or load angle or coupling angle or retardation angle, that is the alpha. So now in synchronous motor on no load with losses, EB is equal to V, EB will not be located in exact opposition with V. So displaced from its initial position by angle alpha shown in figure. So hence the vector difference between EB and V is not 0, but gives rise to a resultant phase here shown in figure. So that is V minus EB, that is equal to IA ZS, that is called ER. This resultant decides that amount of current IA to be drawn to produce the torque. This resultant decides that amount of current IA to be drawn to produce the torque. So now synchronous motor here with losses here on no load, the armature current IA, that is equal, IA is equal to ER by ZS. Under no load condition, alpha is very small, hence ER also very small. Current drawn by the motor is also very small. Current drawn by the motor is also very small. So this is the vector diagram is given the phasor diagram is given in the motor. So see as shown in figure. So supply voltage V and the armature current I, and the phase angle between V and IA is pi, and the resultant current and the IA is theta, and the alpha is the load angle between the, so EB and reference axis is alpha, that is the resultant of voltage. Now synchronous motor on load, as the load on the synchronous motor increases, the load angle alpha increases, but there is no change in its speed as a alpha increases. The resultant voltage ER increases, the current drawn by the motor increases. This current produces the necessary torque which satisfy the increased load demand. Increased load demand. The synchronous motor is the magnetic locking still exists between the stator and rotor. The phasor diagram is shown in figure. Here the angle alpha goes on increasing as load increases. The maximum permissible limit of alpha is 90 degrees electrical. So if alpha is increased by beyond 90 degrees, so magnetic locking between stator and rotor breaks and motor comes out of synchronism. Motor comes out of synchronism. So the motor stops here. The motor stops. So observe here. For 90 degrees, the operation is stable operation up to maximum torque. After that, so operation stator, the motor operation is unstable. Here, the load angle is taken as an x-axis, and the load angle is taken as a the y-axis is taken as the torque. Load angle is in x-axis. Here, torque produced at alpha is equal to 90 degrees is maximum. Alpha is equal to 90 degrees. This torques is called as pull out torque and is shown in figure. This torque is called pull out torque. Angle of retard, angle of advance. The angle with which EB is phasor moves from its initial position so as to give rise to resultant EMF is called angle of retard at load angle. So angle of advance is nothing but here 180 degrees minus angle of retard. Here the analysis of phasor diagram, let alpha be the load angle, armature current is IA, that is equal to ER by ZS, resultant EMF that is ER, and the synchronous impedance is ZS, that is equal to RA plus JX. Yes. Now theta, the resultant angle between the resultant voltage and the armature current, that is theta is equal to tan inverse of XS by RA. So now the EMF that is equal to V square plus EB square minus 2 VEB cos alpha minus 2 VEB cos alpha. So here the angle theta is called as internal machine angle or impedance angle. Internal machine angle or impedance angle. So this is the theta. It is constant for motor. Theta is always constant for motor. Why it is constant? It is depends on the x and r parameters. The significance of angle theta is that it tells us, so IA lags behind here. So theta is tells us IA lags behind the significance of angle theta is tells us IA lags behind ER. So practically RA is very small compared to axis, and theta tends to 90 degrees. So phi is equal to power factor angle between the voltage and current, and cos phi is power factor of motor is working. Here the summary is the performance of synchronous motor on no load, no losses, and the performance of synchronous motor on no load with losses. Synchronous motor on load and analysis of phasor diagram, we have discussed these things.